Let me close the door. Any questions from last class? Can you also close the door in case it's not? Any questions? So in the last class, we dove into detection. So the idea was we wanted to design detectors that had some optimality properties, and then we saw that several different criteria we can define for optimality. So again, just to remind ourselves, the unknown parameter theta in case of detection is only finite possibilities, right? So let's say K hypothesis, and then you observe data related to these parameters, and they're related through the model. And then the detector takes in the data and outputs a decision, right? And the decision is which of the hypotheses it is. And so the detector, we said we can define in terms of the probability distribution, right? So it's probability of outputting different hypotheses or different decisions given what your data is, right? So let's say probability of D equals I means that the detector said it was I. So, right? So, and this is general because it covers both deterministic and randomized detectors, right? So one question was, in what scenarios is deterministic detector the optimal one? That is, you don't need randomization. And are there scenarios where randomization is needed? And to address that question, the very first thing we realized was the use of likelihood ratio, right? And that relates to the notion of sufficient statistic. So we said that the likelihood ratio is all what you need and nothing else. Since most of the class we've done binary detection, in that case it would just be a single number. In the general case, it would be ratio of each of the hypotheses, right? With the, say, one of them, let's say theta 0. So this was the likelihood ratio, and we argued if this is the sufficient statistic, any optimal detector should only depend on sufficient statistic. And so the idea was we can use the likelihood ratio and do a threshold rule. So in case of binary detector, it's only a threshold rule, right? So if it's greater than some threshold, we would say that the decision variable is 1. That is, you're saying that theta 1 is the underlying parameter. Right? So that was the likelihood ratio rule. And then we came up with different criteria of what is optimal and how that optimality will help us decide what is the threshold. Right? Because sufficient statistic, all it tells you is this is enough, but it doesn't tell you how to design the threshold. And that's given by the objective we choose. And that's where we came up with a few possibilities. The Bayesian was a natural one where we also have a prior distribution. And we have cost, right? So the cost is true for both the cases, but we can think of a cost that depends on the decision variable and the underlying parameter, right? So in general, you could have all kinds of arbitrary costs for making each decision when the underlying parameter is something, is one of the theta. So that was the general case. And then we said the notion of risk is one of minimizing the expected cost, right? So the risk, we said, depends on the detection rule, like what is the detector we are using, and it depends on theta. So in case of the Bayesian one, we will condition on that theta, right, what is occurring. And in this case, it would be the expected right, under that detection rule, so delta. So the expectation is with respect to that detector. So that was risk, and the Bayesian risk also averages with respect to the prior distribution. So you also have now expectation of R delta. So when I use this notation, I treat theta as a random variable. So think of it as capitalized, which is nothing but you're taking the expectation with respect to both the data and the prior, right? So you have delta of y, and then you have theta. Now you have the model distribution, you have the prior, and you're integrating over both of them. Right, so it's averaged over both your realizations of your data as well as realizations of the parameter theta. Right, that's the Bayesian risk. And in the previous class, we had just been completing this general case and asking what is the optimal Bayesian rule. And we found that the detector was deterministic. Right, so we'll have a recap of that now and then focus on the general case. So let me erase it because this is just the expectation. And now let's set up the general case. Right, so for the general case, we said let's look at the risk under conditioned on y. So let me just use the same notation here so that we don't. Right, so I'm gonna look at the risk conditioned on what my observed data is. And this is nothing but what we're going to do is looking at the expectation of the cost under both the decision variable and theta, but I condition now on my data. Okay? So I can think of the different possibilities for my decision variable, right, which is nothing but having one of the k hypotheses as the output. So I can look at probability that you decided, or rather, the detector decided that it was the kth hypothesis, and under that, you would pay a price of this much, right? And then you'd also take expectation over theta, right? And you would average over all the possibilities of the decision. Sorry. Is that clear? I've essentially expanded this expectation, and this is nothing but just now I've also conditioned it on what data I observe. And what data I observe is, if I have this conditional distribution, this is nothing but my detector, right? This is my definition of what the detector is. Is that clear? Is this dependent on theta? Is this a function of theta? So what can I do? Could take the integration here, right? So I'm justifying when we wrote the inner product in the previous class. So this is the more detailed derivation. So when I take the integral here, so I can just do that here. So this is now nothing but, again, some cost that depends on k, right? So I integrate out the prior. So this is now nothing but, I can write it in a compact form in terms of, let me call this delta k because the detector is making decision k. And there is some cost that is a function of k, and that's it. Right, and this is more compactly written as inner product. It's intuitive, right? Because if you're calculating the Bayesian risk and you assign a cost for each realization of theta, what you have is a linear combination of those costs. Right, so that's intuitive, but just this is the actual derivation. Okay? Any questions here? Right, and then now we have the minimization of this cost, right? So to get the optimal detector, I want to minimize this inner product, and I put the constraint, this should be on the probability simplex, because delta of y is a probability density, it's a probability mass function, right? It's discrete. So I use this compact notation for that. This is the probability simplex. And we argued in the previous class that it's a property from linear programming, and the intuition is if you have a probability simplex, right? So, sorry, I apologize. My drawing is not always the best. So I have the probability simplex, so delta can take any value in the simplex. Right. And the corners are, the vertices are the ones which just take, right, value 1 at one of the indices. So the idea is, if it only takes value 1 at one of the indices, what is it? Deterministic, right? So those are the vertices, and now you're trying to optimize a hyperplane. So the hyperplane is any thing where you take this inner product and set it to a constant, right? That's the hyperplane. And if you're trying to optimize this, right, the first intersection that will happen is at the vertex, right? So it has to pass through the vertex before it goes to the interior. And so that's why for any problem of this form, the optimal solution is at a vertex. And that's why if you recall in linear programming, there's simplex methods, right, which try to reason about which is the vertex among all the vertices, which is the vertex which is optimal.
Just a question. here we assume that we have a prior over theta, right?
Yeah.
But generally, if we have this assumption that we are coming from the space, isn't it that the decision rule itself should probably be related on data and also our prior? I mean, that delta shouldn't be related also to somehow the
It can't be a function of theta, right? Meaning you can't make your decision based on theta, you don't know theta.
But we know the distribution for the we have the prior distribution, right?
And that will come up here, right? So the cost.
Generally, shouldn't we?
The cost, right? The cost.
Probability of what I mean is, isn't it the case that the decision rule might be like this?
We are deriving the decision rule.
Yeah, but you assume that the decision rule is probability of decision condition on Y.
And we are designing that. That covers all possible decision rules. We haven't made any assumption, right? We allow for any arbitrary decision rule. This just tells you I can make any decision by thinking of it as this probability distribution. Okay, so far we haven't made any design choices at all. This is general.
That means everything you assume is inside that cost, that cost function.
Now the cost is what will help us determine what is the optimal, right? So here I'm optimizing now over delta. Here I'm just setting it up, right? So only I look at the optimal rule only at this point. All I'm doing is computing this conditional probability here, right? I haven't constrained myself to any specific rule here. Is that clear? Right, any decision rule, you can think of it in terms of the conditional probability, right? What is the probability of having a certain output conditioned on my data, right? That's how you can, treat any decision rule. And the deterministic is a special case. Any questions here? Right, so, and that's why, because of the simplex property, what we have is that the optimal decision is given by one of the vertices. So that means it is a deterministic detector. And last lecture we saw that for the binary hypothesis it's simpler, right? So for binary hypothesis, in fact, the decision rule was given by the ratio of the priors. Right, so let me write it this way. For the 0-1 cost. So for the special case when you have 0-1 cost. And you could still go through this exercise and rederive that, but in the binary case, it was just comparing between two vertices, right? So it's not even here, it is 3 hypotheses. If you have just 2, you have to just compare whether this vertex or this vertex. And that made the rule simple. Okay, so in the Bayesian case, randomization buys you nothing, right? So determinism is all what you need. Any questions here? So now let's go to Neiman-Pearson and ask, how does this change when we come up with a different criterion for optimality? And the whole idea was, right, this risk is a function of theta. And you could have a domain of theta and you don't know what the underlying theta is, right? So you can't think about minimizing risk just for a specific value of theta. I mean, that's, that's not robust, because if you only choose one theta and it's a different parameter that the data is actually generated from, you will not get good performance. And so we said there are two possibilities. One is the min-max detector, the other is the Neiman-Pearson. In this class, I'll focus on Neiman-Pearson. Maybe in the recitation, we'll deal with the min-max detector. So in Neiman-Pearson, the whole idea was, if your goal is to detect certain catastrophic events or those that affect human lives adversely, right? So you don't want to miss this detection as much as possible. But at the same time, you want to balance it with having a lot of false alarms. And this trade-off has to be specified by the designer, right? So how much should you tolerate false alarm? We don't know, right? So that depends on human psychology, that depends on how dangerous is this event, the catastrophic event, potentially. So that's the trade-off we need to make. But here we'll assume that the designer has given us this specification. So meaning there is the type 1 error or the false alarm. So by the way, the false alarm is also called type 1 and the misdetection is called type 2. But I'll just limit the terminology to false alarm and detection because I think going from one to another is more confusing. So I won't use it, but if you look at literature, you will also come up with a type 1 and type 2 error. So false alarm, right? So this is wrongly saying that this problematic event happened when it didn't, right? So meaning you're saying that your decision variable is the alternative hypothesis when the underlying parameter was just theta 0, meaning when the null event happened. So this is falsely alarming, and so that's one type of error. The other is misdetection, so where you switch the two. Here you do not end up detecting the alternate hypothesis or the problematic event. Okay, so these are the two kinds of errors. I'll use PF to denote the false alarm and PM to denote the misdetection. So the complementary event for misdetection is detection, right? And that is a good thing. We want to be detecting the alternative hypothesis when that occurs. And so this I'll use PD as my notation. Okay, so just the two types of errors, right? When they're binary hypothesis, you can essentially switch the decision variable and the underlying hypothesis, and we are looking at the trade-off between the two. So I can plot the false alarm and detection probability for different detectors. And this curve is called ROC, or region of operating conditions. Okay, so this is the ROC curve. What are the limits for this ROC curve? Naturally, you cannot go beyond 1, right? So that's a limit. Can I have this extreme point here as a valid detector? That is the 1, 1. Is that achievable? What does it correspond to? So the probability of false alarm is 1 and probability of detection is 1. What is that?
Just always alarming or
Right,
detecting.
exactly, right? So here the decision variable is always 1. Right, so this is trivial. You don't ignore all the data, you always just say this alternate hypothesis happened, this problematic event happened. Okay, so what are the other possibilities? What about this straight line here? So meaning, let's just say I have alpha for my false alarm. I also have alpha for my detection probability. Can I achieve this? What does it correspond to?
Just detecting with a probability of alpha regardless of the condition.
Exactly, right? You just flip a coin with probability alpha for the null hypothesis. So again, this whole line is just a random detector, right? It's data independent detector. Let me call it data independent. So if you want a good detector, what should it satisfy?
Right.
Go ahead.
You go. Raising a hand, I'm sorry. Should be in the upper triangle.
Right, it should be in this region, right? I mean, this straight line is trivially achievable. You don't want it lower than that. So the idea is higher the curve, the better, right? Because you're not alarming falsely much and you're detecting more number of times. So that's a good thing. So it should be this way, but on the other hand, of course, it can't go to this limit, right? So that's why it should be concave, right? So that's a property of any detector, that it should be concave. Okay, so those are some properties we can quickly glean. And now the question is, we can go back to the likelihood ratio detector and ask what properties does it satisfy? So I forget what is the theorem called. Give me a minute. Oh yeah. So we have to first, of course, formally define what optimality means here. I haven't set up the problem. So let me set it up. We'll call it the UMP, or uniformly most powerful detector. Right, so the goal is to optimize for detection probability given a constraint of the false alarm. Right, so you want to ask what is the maximum so I'll also use delta for the detection rule, right? So here I could also, make the dependence on delta explicit. Right, because naturally that depends on the detection rule. So I want to get the best possible detection of the alternate hypothesis given a constraint on the null hypothesis. So I'm only written down for a simple hypothesis. Right, so when I say simple, I mean there is one realization of theta naught and theta 1. More generally, you could have composite hypothesis, meaning the null could be a combination of several different parameters, and similarly for the alternate. In the notes, I briefly talk about it, but I won't be covering it in the class because there it gets a bit more messy to deal with. So just a side note, so keep that in mind when you take a look at the notes. But the idea here is we want to have a constraint on the false alarm, right? And that's what this curve will tell you, because it says now this is my false alarm. What is the detection probability? Right, so each point on this curve will be the operating condition for that detector. So I can set different levels of false alarm and I can get different points on the curve.
But that actually, is it possible to, when the constraint point, right? The constraint here point, right? Or sometimes the constraint in the UMP.
Yeah.
Is it possible that we have, for example, something less than alpha and maximize something here? Or does it's binding, right?
Yes, yes. So it should. I mean, the idea is you will, yes. I guess your question is, can you achieve it somewhere here, right? But intuitively, you should always be able to do better by, going to the, the bound allowed, right, for false alarm, because the idea is it's a trade-off, right? So
always we fix one of them and then maximum.
That's the Neiman-Pearson setup. Okay, so this was the setup, and then the question is, if we have the likelihood ratio rule, is that optimal, right? And if so, what kind of rule would that be? So the deterministic detector would just do this, right? So we'll just rewrite this likelihood ratio detector. So what it will do is look at likelihood ratio, and if it's greater than some threshold, you get that the decision is 1, otherwise you get that the decision is 0. Okay, so this is deterministic, right? There's no randomization. Okay, so now what the result says is that's the Neiman-Pearson lemma. What it says is that this is optimal amongst all deterministic detectors. So if you only limit to deterministic detectors, this one is the optimal one. Okay, and we can actually prove that. So let me call this, let me use the same notation as here. So let me make this equal, right? So just for completeness. And let me call this delta star. Okay, so the likelihood ratio detector, I will label it as delta star. And so the idea is I want to now look at what is the detection probability under the likelihood ratio detector and any other detector. So if both are deterministic, right, I can actually evaluate what this likelihood ratio is. Right, so let me call this region, so the region where y takes these values, as gamma 1, and this is gamma 0. Okay, so the idea is when y belongs to gamma 1, the decision is, and vice versa. So for each one, that is true. Right, I'm just labeling each region by gamma 0 and gamma 1. Okay, so if I want a particular evaluation of this probability, what I need to do is I need to look at the probability distribution, right? I'm looking at it under parameter θ1. And then I integrate this over region gamma 1. This is just identity, right? Ignore the second term at. So this gamma 1, of course, depends on your detector. So let me call it gamma 1 star for the optimal one.
Can I ask you some question? I just want to understand if my intuition is correct or not. Generally, I mean, probably. Is it
So-
like you want to prove?
Can we finish this? Let's finish this. How about that? Keep that thought in for a bit. So all I'm doing is just deriving the identity, right? So ignore the second term. If I want to write down what my detection probability is, right? I'm just integrating over this region, and I'm integrating it over the set where I make the decision to be 1, or the alternate hypothesis. I'm just, the notation is gamma 1 star for that, okay?
Sorry, what is gamma 1 star again?
Gamma 1 star is the decision region for the likelihood ratio detector where it says it's 1. So this would be like y such that, right, delta star of y is 1. Okay, to be precise. And that's natural, right? I can derive the probability in terms of just integrating it over that decision region. Any questions here? So I can do the same for any other detector. It's the same thing, it's just the two only differ in terms of their regions. Can I write this expression for a randomized detector? What do you think? How did I define gamma 1? Can I write this for a randomized one? I cannot, right? Because there is a certain probability. I can't just say in this region I'm always mapping to the decision variable as 1. So this expression I can only write down for deterministic detector. And that's why I'm having this constraint, you see. And sometimes in the beginning it's not obvious. It's like, okay, I can evaluate the probability this way. But it really cannot. If it's randomized, you can't write this expression. Okay, so for both of this, I can just use the likelihood ratio rule for, okay, so for both the terms, I can look at the intersection with gamma naught. And this is still an identity. And this one, I can look at it in terms of gamma 1 star. So just the same thing again. I'm not going to write the term again. This is nothing but the set, right? If you have like two sets, you're looking at what are the exclusive regions. So think of like two sets, right? So what you want to say is where does it differ? If there is the intersection and you're looking at the subtraction, that just cancels out, right? So you don't need that. So all you need to look at is this region and this region. So this is gamma 1 star intersecting with gamma 0 with the other detector, and this other set is gamma 1 intersecting with gamma 0 star. Okay? So it's just identity, I mean, nothing changes. So I can do this, and then these sets don't intersect, right? So that's a good thing now. What I can do is on this set, anyway, it's a subset of gamma 1 star, this likelihood ratio rule should hold. So I can write it as being greater or equal to under the same region, but then I make it this eta, which is the threshold times the density under null hypothesis. So I've just written the first term. And it's also true for the second term because it's a subset of gamma naught star. So the same identical term also is going to be present for the second term. I know it's confusing maybe the first time you see it, but if you think for a minute, this is okay. Right, the first term is a subset of gamma 1 star, meaning the optimal decision region for the decision region for likelihood ratio detector, where the decision is 1. And this one is a subset of gamma naught star. So that's why I can then enforce this likelihood ratio rule and do this substitution. And now this is nothing but, right, this is bigger than so you have eta, you can take that outside. And if you think for a moment, you can argue that this is nothing but the false alarm for the likelihood ratio detector, or greater than, it's not exactly, but you can bound it this way. Okay, and so with this, if you start with the assumption that you're looking at all detectors where the false alarm is at most the false alarm of the likelihood ratio detector, that's your assumption, then you also have that your detection probability cannot be better for any other deterministic detector. So a few steps may be requiring more thought, but the outcome, right, what we wanted to prove was that the likelihood ratio detector is optimal among all deterministic detectors. And the main trick we are using here is to put down the regions. If it's deterministic detectors, I can think of these probabilities in terms of integrating over certain decision regions. And then I have the use of this inequality on the density functions because I have this likelihood ratio rule. So I'm substituting that, and then in a few steps I get the answer. Any questions here? It's a bit tricky in the first go. That's why I want to make sure you understand this. For anyone, this is not clear? Yeah.
I was just wondering if you could explain the step where you add the intersection of like gamma knots. So
think in terms of sets, right? So this, let's say this whole thing is gamma 1 star. And this is another set gamma 1 for the other detector. They would have a region where they intersect, right, the common region. And then they have exclusive regions. In the common region, because it's subtraction, it just cancels away. Does that make sense?
Yeah.
Could you explain one more time for us to quality why the star is bigger than anyone else?
Oh, this is the assumption. Because you're looking at all detectors whose false alarm is at most the false alarm of the likelihood ratio detector. Right? The optimality is with respect to all detectors, I didn't explicitly write down, with false alarm, at most the false alarm of the, right? Otherwise you can't compare the detectors, right? It's not apples to apples. Right, because we compare the detectors with respect to a fixed false alarm here. Here, if you fix it, you can say which one is better. And then we can ask, is it uniformly better throughout for all values of alpha? And that's the uniformly most powerful detector. And what this theorem says, I mean, Neiman-Pearson called it a lemma, right? So it's debatable what's theorem, what's lemma. But anyway, the result is that likelihood ratio detector is uniformly most powerful amongst all deterministic detectors. Meaning it has the best possible detection probability when you fix the false alarm. Okay, so because, and we use the deterministic heavily because we couldn't integrate over fixed regions if we didn't have a deterministic rule. So this is good. So we have optimality for likelihood ratio detector. And in a way, because of the minimal sufficient statistic, it was also intuitive this should be, right? But we still haven't ruled out randomized detectors. So for this, what I'll do is I'll do an example. Any further questions? Is the proof clear to everyone?
So you're saying that there are some randomized ones that are better than this one?
I haven't still come to a conclusion. We'll now look at some.
I wanted to confirm my intuition again. That's my, that PF is like a price and that alpha is like a budget, right? So you're trying to go to supermarket and buy things that maximize your utility in some sense, subject to that one. And then you can think that for each object, you divide the value you get by its price. That's what you did, and you go and find the sum of them that maximize the whole thing, subject to the budget you have, which is alpha. And
Right. You can think of also in the economic terms that way, yes.
I mean, this is exactly that, right? You have that is you're maximizing your PF such that that is your budget. I see.
So in a way, you're like saying, if you tend to say, if you tend towards making the decision to be one more, right, you will pay a price with false alarm because you're also going to be wrong under the null hypothesis more number of times. So there is this inherent trade-off, and that's why this is a concave curve here. Okay, is that intuition clear to everyone? Any further questions? So we'll now do an example and see whether we need randomization here. So quite a simple example. So we'll look at the coin, and the null hypothesis is, so I'll write null hypothesis this way, right, H naught, is that it's a fair coin. And the alternate hypothesis is it's a biased coin. So fair coin would have, in my setup, both head and tails with equal probability. Okay, so biased coin just has, I guess here, what am I saying? Heads, just has heads. Okay, so you don't know, right? So I don't know if the coin has on both sides heads or it has only, it has both head and tail, right? So those are the two possibilities. And I just do one coin flip. So I just have one draw and then I want to determine what hypothesis it is, right? So now I have my Y could be heads, could be tail, right? Those are the two possibilities. So my decision rule intuitively, right? So let two possibilities, right? So this is very simple because you just, all you are having is two different realizations of your data. It can be head or it can be tail, right? Those are the only two possibilities. So now the question is, what is the decision rule for these two cases? What should I decide if I see the outcome to be head? What should I decide if the outcome is tail? So what should I decide if the outcome is tail?
Fair coin.
It's fair, right? So if it's tail, it's very easy, right? So if it's tail, I know that this is 0. Yeah, right? But if it's head, what should I do?
Half probability fair coin, half probability biased.
I mean, it depends on my criterion, right? I haven't told you what optimality criterion should I satisfy. So it depends on my false alarm. If I'm under the Neiman-Pearson setup, it depends how much false alarm am I allowing you to do, right? So, and now you can see the trade-off here. So the intuition is, if you allow for a lot of false alarm, right, I can, what should I do? So let's again do the same ROC curve. So again, I can have like a trivial detector here that always says that it's alternate hypothesis, or I can have it, somewhere in between, right? So again, it's the same kind of, I would ideally want some concave curve here, right? So this is what I would need. And now the question is, depending on what alpha I choose, this probability of either saying 1 or 0 under heads, that'll be determined by my alpha, right? So now the question is, how do I go about designing this? So let me just write down the likelihood rule here. So the likelihood ratio, how can I compute this? So again, there are only two possibilities, right? So what are the two values the likelihood ratio takes? If it's tails, what's the value of likelihood ratio?
0.
0, right? Because that's impossible.
And for heads it'd be 1, or it depends.
So here I said probability half, right? So if it's half, then what is the likelihood ratio? So there's half here and 1 here, right? So so let me write it down. What's the probability of heads under theta 1? What is it? 1, right? Right, it's completely biased towards 1. What's the probability of heads under theta naught? Half. So what should the likelihood ratio be? 2, right? So yeah, so now I can ask the threshold rule with likelihood ratio detector. So let's say this is my threshold rule. So I can choose eta for different values. So I can choose, so what if I choose eta to be 0? What does it correspond to? So meaning, I mean, when I say this is the likelihood rule, in this region I will say my detector is 1, right? That's fine. So if I choose my eta to be 0, what kind of detector is that? What are the values the likelihood ratio takes?
It's always going to be the game.
Right, it's always going to be just the alarming or detecting. So that's this point. Right, so eta equals 0 means the decision is always just 1. Right, so it's a trivial detector. So I can't, so it's not useful if I want to trade off the false alarm because this is trivial. So what if my likelihood ratio is bigger than 2? I guess that's also easy, right? So what is it in this case? It's 0, right? It's always going to be 0. And what point do you achieve in this case in the region of region of operating convergence?
Could you please write also the alpha and the PF?
Yeah, okay, so what do you think is the alpha here? That was this point, right? So alpha was 1.
But this is among everything that has alpha 1 pieces, but it's still optimal, right? I mean, in some sense, right?
Only among deterministic detectors. So we are just, all we are doing now is just setting different values of eta, right? The threshold in the likelihood ratio detector and seeing what's the outcome, right? What are we getting at? Right, so far I haven't addressed any optimality. I just want to plot the region of operating conditions on the curve for this likelihood ratio detector. Okay, so this is one point I could realize. So if I chose eta to be greater than 2, what do I get?
0 and 0.
This is 0 and 0 here, right? This other point. What if I, let's say, chose eta to be somewhere in between, right? So let's say in this open set 0 to 2. What am I achieving here? What is the detector doing if I choose my threshold?
Why H is decision is 1 or 1T decision is.
Right, exactly, right? So here I'm always saying it's 1. If I see heads, I'm saying it's the alternate hypothesis. If I'm seeing tails, I'm saying it's null hypothesis. What is alpha in this case? So I can write this down, right? So if y equals heads, it is 0. Or the other way, sorry, the other way, right? So what's the alpha in this case?
Doesn't the alpha depend on your prior probability on like how many coins are fair versus?
So there's no prior. This is not Bayesian. This is frequentist, right? There is no prior defined here. Right? There is some fixed hypothesis. And here I've just told you these are the two hypotheses. Okay, but I don't need the prior. Right? The false alarm is the probability of saying it's hypothesis 1 when it's actually hypothesis 0. Right? So there's no prior defined for the frequentist setting. So the alpha, right, in this case is making the error that we have a biased coin when it's actually fair.
0.5.
It's half, right? Because there's half and half probability you see heads or tails, right? So your false alarm is half. So what point is this in the region of operating conditions, ROC curve? So when do you miss the biased coin in this case? How many times do you miss the biased coin on average?
Half the time. Oh.
Right? Because that's when you don't know, right? You're only saying half the time you see heads that it is biased. So the other half you could miss. Right? So you only achieve these points. So can I achieve anything else by using only deterministic detector?
But when you have a bias coin, you will always see heads. And even if you don't see a bias coin, when it comes heads, it's certain that you won't miss any bias coin. I mean, you can never miss a bias coin. That's
a good point. So it's actually not half, right? So it is, what is it? It's actually 1. I mean, you may see heads half the times, right? But all the heads from the biased coin are not missed. Is that clear? So it's actually half and 1. This is achieved. Right, so I could achieve 3 points on this ROC curve. This one, this one, this one. So what if I want to achieve other points? What should I do?
When you see heads randomized between the two?
Right. Exactly, right? So you cannot do away with randomization here. In the Bayesian case, we could say that you don't need randomization. But here, if I tell you that the false alarm is, let's say, something like 0.1, right? I cannot do the trade-off just using a deterministic rule. And so that's where randomization is needed. So,
if, for example, if you get this continuity, then that's it.
Yes. So that's why it's only needed when you have this likelihood ratio being a discrete or having some atomic measure, right? So if it has some discrete jumps, then you cannot uniformly cover the amount of false alarm region you need, right? So that's when randomization is required.
So you select for discrete case, you select all these points and then you just convex.
So in a way, randomization helps you kind of, right, cover also the region between the two. So that's why randomization is needed.
Who select alpha?
The alpha is always selected by the designer, right? And I think I briefly commented in the previous class that it's dependent on, right, how serious is this alternate hypothesis if we miss it, and how much do people have tolerance for that false alarm, right? So all kinds of design considerations. But we treat alpha as given to us, and we try to solve the best possible scenario. Okay, so the idea is now if you had like the likelihood ratio to be, right, having discrete jumps like the ones I showed you here, right? So let's say I have something like this, and sorry, not like this, sorry. I mean, a discrete jump would be an atomic jump like this, okay? So if there are discrete jumps like this, I can't just do a thresholding, right? There is non-zero mass at one point. So that's where I would need randomization, right? So randomization is needed. Okay. So when you have atomic measures on your likelihood ratio, you would need this. So now the Neyman-Pearson detector with randomization would be of the form, you have the likelihood ratio, right? So now you have three cases. If it's strictly greater than eta, strictly less than eta, and then equal to eta. So if it's continuous, these two are kind of just together. You don't have any finite mass, non-zero mass at the equality one. But if it's discrete, then you would need this, right? So the idea is in this case, if it's bigger than eta, you just declare its alternate hypothesis. If it's strictly less than theta, you declare it as null hypothesis. And then if it's equal to eta, you declare alternate with some probability, right? Let's say this probability is gamma of y. Is this clear? So how should I design the gamma of y? So how should I have the false alarm, right? So what is the false alarm going to be?
You should set it like exactly to alpha, so that will like maximize your probability of detection while stay under the restraint.
Right, so that's the Neyman-Pearson rule. So the idea is you want to look at the mass, right, like what's taken up by this region and what's the slack, right? So in the sense, what we did here was there is some mass with respect to, if you chose any detector here, you can kind of come here, right? But you want to do something in between. You want to trade off between rather randomize between these two strategies. So in the sense, you're now randomizing between this point here and this point here. Right, so strictly bigger than eta and then strictly less than eta. So how much is the probability mass in those regions? And the slack that's left to cover the false alarm, we will use it with randomization. So that's the intuition. For the exact expression, let me see. I'll just, yeah, so I can think of gamma of y as this, right? So alpha is the false alarm I need, but then how much is this false alarm covered by this region? Oh, sorry, this region, right? So, meaning I'm saying that my likelihood ratio is strictly bigger than alpha, bigger than eta, and under null hypothesis. So if it was continuous, I would just set this to be equal to alpha. But because it's discontinuous, I cannot, right? So there is that slack, but then I should normalize this with a probability you actually realize this value, right? So that's why you normalize it with the probability that the likelihood ratio takes the value eta and under the null hypothesis. Okay, so I'm just like kind of making sure I allocate the right probability measure for the event. Okay, so it's intuitive when you think of it that way, right? So if a likelihood ratio was continuous, I would just set this quantity to be equal to alpha. But because I cannot do that, I look at that slack, what's left. But I have to normalize it by the probability that you actually hit this atomic measure, meaning where likelihood ratio is exactly equal to the point. Okay, so that's how you look at the randomization. And naturally, this randomization is dependent on alpha, right? So this value of alpha will decide how much you should randomize. Any questions here? Right, so for Neyman-Pearson, the likelihood ratio threshold detector was optimal amongst all deterministic detectors. But now if likelihood ratio has atomic mass, we have to have this randomization to be able to handle any arbitrary false alarm requirement.
This is optimal among any other.
Yes. Right, so now among all possible detectors, including randomized detectors, we have optimality. Which is intuitive, right? So if you have discontinuity, you have to randomize between these 2 points, right? So you cannot kind of, in the sense you want to randomize amongst like the 2 detectors on the 2 sides. That's one way to think about it. Any questions here?
And just do the reverse also, right? I just want to make sure everything, again, for example, minimize PF subject to the other one, for example, achieving.
You can just switch the theta naught and theta 1, right? So the idea of why we think of the null hypothesis as the one with constraint is that's the normal operating condition, right? And the alternate is this anomalous or unusual event. So, and it's up to the designer to say what's normal and what's unusual, right? So, as I said, there's a lot of design specifications that goes into setting up this Neyman-Pearson problem. And when we talk about practice, it's in fact not binary hypothesis. You can have lots of different hypotheses. You can have composite hypotheses, right? Meaning normal can be many different kinds of normal conditions, not just one kind, right? So you have all this complexity. So that's why in general you wouldn't have such nice closed form solutions. Right? But this is
you assume that the data comes advanced, everything. This is the all the information we have, and that is the
Yes, and I'll address that in a minute. That'll be the next thing, in fact, we'll deal with. But any questions? Okay, so the next point is exactly kind of following on that thought, right? So we are so far assuming we have some amount of data and we are making the decision, right? So this is also called passive detection or passive learning, right? So I have my data all collected beforehand, I'm making the decision. So what if like data were to come online and you could sequentially make this detection, right? So I'll just introduce it in this class and we can go into details in the next one. And for this, let me motivate with a simple example. Let me say my null hypothesis is normal distribution, standard normal distribution. My alternate hypothesis is also normal distribution, except it has mean 1. Right? So one of the simplest cases we've looked at. Right? So you have like these two distributions. Right? You have one centered at mean 1, and now you have another centered at, right, both are equal. Let me draw better. Then you have the other centered at mean 1. Right, so I can collect a bunch of data, decide whether it's really mean 0 or mean 1. Right? But suppose I'm collecting data and let's say I see the value 3. What should I decide my outcome to be?
More weight towards alternate hypothesis.
Right, so I mean, it's highly unlikely it would have come from the null hypothesis, right? So remember the Gaussian tails, you have exponential decay of probability, and this is far off, right? So let's say you get lucky and you see 3 as you're randomly drawing samples. Should you really go further ahead? Again, depending on what your requirements of error are, probably not, right? And this kind of shows you how if you allow your decision rule to be sequential, you can decide whether you want to go ahead and collect more data or you think you're done, right? Let's say your error constraints are all satisfied. You can just say, okay, now I'm sure I'm done. I know all these are within errors and I can tell you the decision. And that's what the sequential rule gives you, that ability. Right? You don't have to collect all the data beforehand and to make the decision. You can keep collecting data and each time revise your decision. And now the decision is 3 things, right? So first of all, there is the one whether I should continue or I should stop. Right? Those are the 2 possibilities. And if I were to continue, I'm not making any decision about whether it's hypothesis 0 or 1, right? Instead, when I'm stopping, that's when I make my decision. Right, so whether it's...
So there is a cost related to obtaining data?
Right, so now the question is, how can I come up with a problem, right? How do I formulate it? I could think of it as cost of collecting data. I could think of it as the time. What is the shortest time with which I can make a decision, right? That's called quickest detection. So, again, now I have a whole range of possibility to set up this sequential problem. But so far we didn't explore this dimension, right, of whether to decide to stop and make the decision or to continue. So now we have one more dimension to our decision making. And in practice, this would come up all the time. As you're starting with doing a learning problem, you don't know how much data is needed. You may need to have it annotated by somebody. You may need to do experiments, right? So the one that's sequential detection can be very useful because you don't have to decide beforehand, and you can decide as you go along on what is the minimum amount of data needed to get certain error constraints. Okay? So in the next class, we'll look at how to design optimal rules for this and to look at Waltz analysis. I think that dates back to the 40s or 50s, something like that. I forget. It's an old rule, but it's very beautiful, at least to me. Good to see you.